In the interest of time, I'll start introducing Andrei. It's a pleasure to have Andrei Gruzinov here today from NYU. He started his life back in Moscow, so he's a real honest-to-God Russian plasma physicist. Which means when you read Landau and Lifshitz and they say affect the trivial elliptic integral, and even to the most casual observer, they're talking about Andrei, not me. After getting his undergraduate degree in Moscow, he then went to the University of San Diego, joined the plasma group there, and under Patrick Diamond, wrote a thesis on turbulent, nonlinear turbulent dynamos. Okay, so hardcore plasma physics, the kind of stuff you find in tokamaks. After that, he went on to the Institute for Advanced Study, where he started moving in more astrophysical directions. He talked about things like GRBs and CDAPs and even nuclear fusion rates of the sun. And one of his most cited papers is actually on something completely different. It's on cosmology, where he has some new way to generate, well, not new anymore, an additional way to generate inhomogeneities after inflation. Following his time at the IAS, he moved to NYU, where he joined the Center for Cosmology and Particle Physics, where he's been ever since, and working primarily on astrophysical plasma physics, the physics of high-energy compact objects, and just for something fun to do on the side, I guess, a non-standard inflationary cosmology. Without further ado, here's Andrei to tell us something about pulsars.
Okay, so I want to talk about pulsars today, mostly pulsar theory, but to begin with, let's recall the observables. This, of course, everybody recognizes as Crab Nebula, as seen by Hubble. Various colors are showing different lines, and therefore different elements. If we zoom in a little bit and switch to X-rays, we see yet another famous picture, which is loosely suggestive of some combination of outflows and radiation. And for the curious, if you go online and ask for something like high resolution graph, this thing can be animated giving time dependence, and the time dependence also strengthens this feeling of some outflow combined with rotation. To further zoom in, we go to the time domain, and in the time domain we discover that there is this 30 millisecond pulsations all the way from radio to optical to X-ray to gamma ray to very high energy gamma ray. And maybe Chris tell us, do they have TeV? I'm not quite sure. It goes at least to 100 GeV. I'm not sure TeV has been detected, so, but it doesn't really matter so much. It is certainly there if 100 GeV is there. Okay, and the shape of the pulse varies. As you see, one peak, first peak can be higher, second peak can be higher with considerable emission between peaks. And like I said, Crab pulsar emits all the way from radio to very high energy gamma rays. Crab is somewhat unusual because in Crab emission is actually dominated by X-rays. Usually emission is dominated by gamma rays, but as you see, there is a healthy amount of radiation throughout the electromagnetic spectrum. These are some newer results from Crab from Fermi. Again, this is emission about 10 GeV here, 10 GeV. So it's a gamma ray pulsar, Crab, as many other pulsars. It gets totally crazy when we go into the radio, because this pulse shape, which we have seen in the radio, was just the integrated shape, meaning you accumulate emission over many periods and average it out. But in fact, for individual pulses, you can resolve shorter time scale, and then you get mega-Jansky nanosecond long pulses, giant pulses from Crab. If you just use the time duration of the pulse to estimate the size of the emitting region, you can then calculate the effective temperature, and it comes out to be above, well above Planck temperature, of course, simply meaning that it must be done not by single particles, by some bunches of particles, some kind of in-sync coherent emission of particles should be taking place somewhere in a crowded atmosphere. The source, of course, conventional wisdom is that the source of all this pulsed emission is the source, I mean energy-wise, is rotation energy of a pulsar, and so the rotation frequency of the pulsar as a function of time decreases. This energy supposedly goes somewhere, and in case of Crab, in fact, radiation takes up less than 1% of this spin down energy, which follows from direct observation. So spin down for Crab is a order a few times 10 to the 8 per second, while emission was probably something like 10 to, let's say, a few times 10 to 36 if we break it. And in this respect, actually, Crab is somewhat unusual. So here, Crab would be this point. What's shown here is for Fermi gamma ray pulsars, gamma ray luminosity as a function of the spin down luminosity. Okay? As you see, Crab is somewhere below where it should have been, because if I try to ignore this theoretical field, it's too complicated because it's two lines. Let's try to draw one line. It would calculate past all these points, and this one line will be something like 10%. Roughly speaking, 10% of spin down goes into gamma ray emission, and this is the interesting number for us to remember for the future. In this respect, Crab will be the exception, which will be much higher. And so this was just a quick introduction into the subject, that there are these spinning down neutron stars. They do miracles in terms of what they emit, and we will try to understand these miracles. So we will attempt pulsar theory, and of course we are not the first. We have good call them collaborators, which try to solve this problem, starting with Graham, Goldreich, and so on. But let's first ask, really, is the pulsar theory possible at all? Because I recall, approximately recall, it has been some 10 years ago probably, this dialogue. The context was some new data on GRBs appeared, and probably GRB polarization or something, and Bakal, with his usual enthusiasm, addressed John Bakal addressed Bob-Baczynski saying, okay, with all this new data, we will now have a theory of gamma ray bursts. To which Baczynski replied that, in fact, in most of high-energy astrophysics, the objects seem to be well too difficult for any theory. And indeed, roughly speaking, Baczynski must be right? We have all these fancy names: quasars, blazars, QPOs, GRBs, pulsars, magnetars, and so on. I wonder who invented this name, magnetar. So we have all these fancy names, and for each of those we have some fuzzy idea what might be going on, but in almost no cases can we really calculate. We can think up models, but not something close to whatever, let's say, light curves of a binary or something, which which then nicely are reproduced by Kepler. Nothing like this exists for any of those. So it's not obvious whether or not pulsar theory is possible, and maybe we are wasting our time here. But there is hope, I think, because even for these quasars and some regimes, say thin accretion disk, since all black holes are the same, they are just curved, we sometimes radiation part of the problem becomes trivial, and the gravitational part of the problem is exactly calculable. And so, for example, for thin accretion disks, we can sometimes predict the expected spectrum to such an accuracy which allows, at least for some people, it allows to infer this the rotation period of the black hole. So, in fact, pulsars, not that I think, but pulsars are thought. Conservative point of view is that pulsars are in fact simple. Namely, it is believed that if I just take a perfectly conducting, magnetized, spinning ball, if I make this thing 10 kilometers, if I make it whatever, 30 hertz, if I magnetize it to a few times 10 to 12 Gauss, it is thought that just this simple thing spun out in vacuum will produce all crap miracles. Maybe to have exact matching of light curves, I will have to adjust the surface magnetic field, but that's fine. That's not the real heart of the problem. The heart of the problem is that it is quite possible that surface physics is not that important here, and that in fact just spinning, magnetized, conducting balls are doing all the, or most of what we see in pulsars. So there is hope that some form of pulsar theory is possible. So let's, before we do our own pulsar theory, let's recall what's been done. Classical pulsar theory, its main message, coming back to mostly Goldreich and Julian, Wagner, and other people, the main point of this classical pulsar theory is that pulsars are not magnetic dipoles. They are in fact surrounded by not vacuum. And they also wrote some equations actually. So this is the main paper. So pulsar electromagnetic field is not a vacuum field. The point of this paper was that fast spinning, strongly magnetized, conducting balls will not tolerate vacuum around them. And so in this paper, some equations were suggested, but later on, these equations were written much better than by the original authors, so I will do equations later. But the main idea is that it's not magnetic dipole. You have to somehow treat the plasma around the spinning magnetized conducting balls. But like I said, they wrote some equations. They wrote equations because they were pioneers, so their equations, as you see, are ugly. Our equations will look much better because we have more time. Not only they wrote equations, they drew solutions. So let me, since this picture will come again and again, let me carefully explain what it shows. This shows the so-called axisymmetric pulsar. This is radius, this is height. This little thing here is 1/4 of the neutron star. These things, usually people call them magnetic field lines, but let's not fool ourselves. These things should be thought of as magnetic surfaces. Namely, these are some surfaces of revolution as intersected by the phi-0 plane in cylindrical coordinates. Okay, so this is, they rotate this whole figure, then this thing becomes a neutron star. These things become some surfaces of revolution, and the statement is
that magnetic field line lies on these surfaces of revolution. In particular here, the field line just goes like so, on the so-called closed field lines. There are also open field lines which run from the surface of, so closed field lines run from the star to the star. Open field lines run from the star to infinity. And the field line itself, as I go up, rotates like so. Okay? So these are magnetic surfaces on which magnetic field lines are lying. Now the boundary between open field lines and closed field lines is the light cylinder. If a line crosses the light cylinder, it goes all the way to infinity. If it does not cross the light cylinder, it goes back to the star. And this is the main achievement of Andrei and Julian, is that they kind of proposed this picture that once that on those open field lines there is an outgoing pointing flux, because there will be an electric field going like so, there will be magnetic field going like so, electric field and magnetic field is pointing flux like so. So the spin down power of a pulsar is lost by outflow of pointing power along this field line. So in particular, there is non-zero spin down power for an axisymmetric pulsar, which is of course zero for in vacuum, right? In vacuum, a magnetic dipole rotating around its own axis doesn't radiate, because rotation around its own axis is ill-defined. Right here, because of the presence of charges in the atmosphere. Okay, now it's important for future to recall that this picture was, I cannot recall unfortunately Goldberg's original expression. It was not calculated, it was, how do you do it, when you pray to God and by revelation. Okay, so this picture comes from revelation, not from calculation. And this revelation, the cost of this revelation was very high, because the authors are Goldberg and Julian, so they have a lot of respect. And this revelation dominated the field for the next 40 years, and it turned out to be correct. We should remember that we should ask equations to do revelations, not our brains. Our brains are too weak. So this is wrong. Just plain wrong. Although, like I said, but I spent so much time explaining that he got a lot of it right. So, but since he obtained this picture from whatever, not from solving equations, the picture itself is wrong. So this is just a simple cartoon. This is another important paper in this business. It explains why this spinning magnetized conducting ball will surround itself with charges even if it starts rotating in vacuum. At this place probably you know a lot about it, but just let me remind you quickly anyway. The idea is rotating magnetic field. Magnetic field is observer dependent. So if you have rotating magnetic field, to some observers it will be electric field. The electric field itself will be of order, let's say 10 to 12 Gauss multiplied by beta, beta being the surface velocity in units of the speed of light. Take this 10 to 12 Gauss, reduce it, let's say, to 10 to 11 Gauss for electric field. So you have 10 to 11 Gauss electric field, multiply it on the size of the neutron star, 10 kilometers, you get yourself a potential drop which is way above MeV, right? Way above the electron rest mass. Such potential drops, you don't even have to think further. Such potential drops will not be tolerated, because the minute you introduce just a little probe charge into this huge potential drop, some cascade will result and the hell will break loose. So you will populate the entire outer region of the rotating magnetized conducting ball with like what do you call this? In fact, all those people even use the same terminology. They use words like sparks. Okay, Ruderman's favorite phrase, sparks, if we get or whatever. So it's the same as this lightning phenomenon, basically. Large potential drop will find their way to this charge. Okay? And yet, this classical theory was clearly insufficient because what I said was not a full theory. It was correct ideas about what full theory should be. And in fact, observers were complaining that understanding of pulsars is hindered by the fact that the previous slides were words rather than precise calculations. So they complained that electrodynamics was not treated in a self-consistent way. Even whatever, 30 or so years after, or 20 years after the original papers were written. So then came what we can call neoclassical pulsar theory. It was just formalization of the classical pulsar theory. It's called force-free electrodynamics. And the idea itself just mimics what Goldreich and Julian have been proposing. So what's the idea? We have to describe electromagnetic fields in the presence of charges. So we are dealing then with plasma physics, but plasma physics by definition is Maxwell plus charge motion. Right? To solve Maxwell equations, you need to know currents. Currents are moving charges, so you have to treat simultaneously the electromagnetic field and the motion of charges. This is called plasma physics. Plasma physics is horrible. Turns out that just combining these two is way too complicated. But in the case of pulsars, the idea of Goldreich and Julian was that our charges only carry currents without carrying any energy momentum. Okay, that was the idea. Because right, for the electron, charge is considerable, but mass is nearly zero. So those people said maybe our electrons are moving in such a way that they provide currents without providing any stress energy tensor. So T mu nu is purely electromagnetic, and yet J mu, the current, is not zero. Okay? So this then is the idea of this force-free electrodynamics. It's electrodynamics, Maxwell theory, with currents, but with T mu nu dominated by the electromagnetic field. So here it is. Let's now become purely formal. So this is the proposal then to be checked. Maybe we can describe pulsar magnetosphere, the electromagnetic field around pulsar, by solving Maxwell equation. Now to solve this Maxwell equation in the 3+1 split becomes just this. Remember, we don't have to write the other two. The other two are just initial conditions, which will be sustained by these equations. But to solve Maxwell equations, I need to know the current. So here is then the suggestion. Write the current just in terms of electromagnetic field. Okay? Since we are postulating that the motion of charges is dictated by the electromagnetic field is so strong, it tells the charges what to do. The charges don't talk. There are no degrees of freedom for the charges. Okay? So here is the idea. Write down the expression for J in terms of electromagnetic field only. Now the original system, of course, is Lorentz invariant, and so a good way, this is not how it was done, but a good way to think about this. Suppose this is my test. Write down Ohm's law. Ohm's law is what gives current, but my Ohm's law should only depend on E and B and on nothing else, and it should be Lorentz invariant. So at this point, let's play Dirac. Just write down some equation which is permitted by the symmetries and see where it leads us. So here is how it works here. After some attempts, you can write down these two equations. One of them is this force freedom condition. This just means that the net force on a current is zero. Here E naught is the proper electric field. It's the electric field in the frame where electric field is parallel to the magnetic field. If you wish, it's a certain combination of electromagnetic field invariants. Namely, this equation just says that component of electric field along magnetic field is zero. And this is the other equation. So that's then the proposal. Solve this combined with this. Now, if you just look at these two equations, you immediately have a problem. I mean, you can write down anything, but it's not obvious you can solve it, right? What you can solve should have correct Cauchy problem. That is to say, you need to make sure that for a given initial conditions, your equations are sufficient to calculate future electromagnetic field, and they should do so unambiguously. So the surprising part is that this plus this do allow Cauchy formulation. Before I go to this Cauchy formulation, let me explain more physically what this thing means. So I solve this plus this. So what is the meaning of this Ohm's law? So this Ohm's law in force-free electrodynamics is very simple. Let's do a little exercise in Lorentz transformations. Go to any event. Event means point in space-time. At this event, I will have some electric field, some magnetic field, and some current. These are 3D vectors, and therefore how these vectors are aligned depends on who is asking. This is frame dependent. The orientation of 3 vectors depends on the frame. Now, at each event, I can go to a frame where electric field becomes parallel to magnetic field. Let's do so. Then I will have electric field along magnetic field, and I will have some current. So far I have done nothing. So far I have just defined what I call a family of good frames. Why is it a family? Because a boost along common direction of electric and magnetic field still leaves electric field parallel to the magnetic field. But so let's work in the family, in one representative of the family of good frames where electric field is parallel to the magnetic field. Then this Ohm's law of force-free electrodynamics just says, in a good frame, electric field vanishes and current flows along magnetic field. Now this immediately says, this physical formulation of Ohm's law immediately says that there must be something about it. It looks right. Right? Because remember, we have very strong electromagnetic field. If I have a very strong electromagnetic field, then surely in a good frame electric field will vanish. Because the typical value of the electric field is enormous. So if in a good frame electric field does not vanish, then it will accelerate charges like crazy along the magnetic field. Because magnetic field, if magnetic field is perpendicular to the electric field, it will not allow charge acceleration. Charges will just spin. But if I have electric field along magnetic field, charges will accelerate like crazy along it. So the first requirement of force-free electrodynamics, that electric field should vanish in a good frame, seems to make sense. The second requirement is even more obvious, because surely if I have charges in a very strong magnetic field, they will mostly move along the magnetic field. So currents will be mostly flowing along the magnetic field. So force-free electrodynamics looks perfect. It looks like for strong pulsar-like fields it should apply. So why don't we just go ahead and solve it? So this is what people have been solving in their computers. Maxwell equations. This is this same Ohm's law. So this is why I spent so much time justifying it. In this 3+1 split, this Ohm's law looks terrible, which is, by the way, another sign that this theory must be correct, right? Einstein equations in a particular frame look terrible, but in physics, geometrical formulation, they are good. So this is the same story. This looks terrible after 3+1 split, but the physics behind it is very simple. Current along magnetic field in a good frame. So this is clearly a good Cauchy problem. Time derivative of E, time derivative of E are functions of E and B only. You give me E and B at 0 time, satisfying this constraint. I put this into my computer, calculate future electromagnetic field. So we should apply it to pulsars. These people were the first to do so. And they, as you see, calculated something which is quite similar to Goldreich and Julia. Other people have improved it, even calculated some exact results for this pulsar magnetosphere in particular. They have calculated for the first time the spin down rate of a pulsar. You would recall dipole would be 2/3 of this expression. This is the axisymmetric thing, which should have been 0, because that is 1. So this was still axisymmetric pulsar. Other people have done non-axisymmetric pulsar and provided spin down rate as a function of the inclination angle between spin axis and magnetization of the neutron star. So it all looks right. Okay? So it looks like it has been done some, so this probably should have been like 4 or 5 years ago. So it looks like it has been done. This is not true. This is all wrong, like I said. So now let's go to modern pulsar theory. The main message is this post-free electrodynamics is in fact incorrect. By incorrect, I mean incorrect, wrong. It follows, therefore, that both classical and neoclassical theories are seriously off as applied to pulsars. And in fact, if we were more careful, we should have seen the hints of it. So let's look again at this plot. Spin down rate, gamma luminosity, which is about 10% of spin down rate, sometimes even 30%. What is the prediction for gamma ray luminosity of post-free electrodynamics? Quasi-symmetric pulsing in particular. The prediction is 0, right? All power is emitted as large-scale pointing flux. Okay, so in particular, for this axisymmetric pulsar, we have steady large-scale pointing flux. Do inclination, doesn't matter too much. I have 30 Hertz electromagnetic, large-scale, large electromagnetic wave. So, of course, people who developed this post-free electrodynamics were well aware of the fact that pulsars pulse, that they emit gamma rays and stuff like that. So they were saying something like this. This large-scale pointing flux somewhere, somehow gets converted into gamma rays. That was some dissipative effect on top of this ideal electrodynamics is what's responsible for this observed correlation. Besides, it was known from pulsar wind nebulas that a fair fraction of the pointing flux better be converted into electron-positron pairs because those probably are responsible for pulsar wind nebula emission. And so this was kind of swept under the rug. We were thinking, well, maybe there is some dissipative correction on top of this post-free electrodynamics, but who knows? So let me now give you what I think is finally the correct theory of pulsar electrodynamics. Somewhat, the name is bad. Maybe we will change it. Strong field electrodynamics. The name is bad because it has nothing to do with QED. They use these terms in QED, but this is not early Heisenberg. This is still whatever classical theory. But so anyway, we will stick to this name. Some generalization of post-free electrodynamics, strong field electrodynamics. The results of it that for an axisymmetric pulsar, 50% of the pointing flux is in fact damped. How this damping in the vicinity of the light cylinder, it turns out, this damping must go into pairs and into gamma rays, dividing 50%, say, by 3 pairs, pair acceleration and gamma rays or whatever. I get 10%, which is roughly what I need. But speak up.
Isn't that generally too much?
What's that?
Isn't that generally too much?
50%?
Yeah.
So, like I said, qualification here. This is for axisymmetric pulsar. 50% of pointing flux disappears. Now, it disappears into something. Now, because strong field electrodynamics, as you can guess, will be just some dissipative correction to Pulsar electrodynamics. Now,
well, no, the question is very simple. That if generally in your calculation 50% dissipates, you would expect 40, 90, 25% goes to gamma ray.
right, I would expect 25%.
Which is not generally the case.
This is not generally the case, yes. Some of them, like I said, are something like 150%, but this would be the record holder. It can be 150% because they postulate emission into 4 pi. Some of them are as low as Crab, which is about 0.1% or something. The line itself is roughly 10%, so of course this should be taken, this is too large, maybe non-axisymmetry plays a role. I don't know how to distribute this power between gamma rays and pairs, because remember, this occurs in the outside of the light cylinder. By the time, slightly outside of the light cylinder. By this time, the plasma is rarefied enough that gamma rays, that pairs can carry a lot without inverse Compton scattering those guys, right? So this requires, this would be the future work. To begin, in the meantime, let's just appreciate that there is now a true theory. By true theory, I mean something whose result is independent of who's doing it, which predicts 50%. This 50% for axisymmetric pulsar, so we will have to wait probably for Anatoly to see what this 50% becomes for different inclinations. How it is distributed between pairs and gamma rays, we don't know yet. Let's see. So, what was wrong? So the other thing is, the need to replace, because remember, this post-electrodynamics seemed so good, so meaningful. Why should we replace it with something? Maybe we should better understand observations or whatever. In fact, the deficiency of post-electrodynamics was known for a long time. Those people who produced this picture, for example, when they were calculating the magnetosphere of the axisymmetric pulsar, they in fact imposed by hand a certain boundary condition in the equatorial plane outside of the light cylinder. Okay, light cylinder is where rotation is speed of light. Right? Remember this Wolfgang-Julian feature. If you cross within light cylinder, you are closed. Outside light cylinder, you are open. This is light cylinder. So, in fact, this picture was obtained, when I say it was obtained from post-electrodynamics, I am not being totally accurate. It was obtained from post-electrodynamics plus a certain boundary condition in the equatorial plane. The boundary condition in the equatorial plane, in fact, is the condition that the field line does not close here. Okay? So this is, as far as I can judge, this is pure sociology. Because Waldreich drew it like so, people who later calculated it by hand did not allow field lines to terminate beyond the light cylinder.
Well, Goldreich consciously tried to generalize the Weber-Davis theory to the relativistic case.
Right.
And, you know, those guys were at the same place he was. And I think the picture was strongly influenced by
yes, this is what Peter admits.
our picture of the solar wind.
Yes, absolutely right. He admits that, right. So, but for us at this point, the point is that he might have had his reasons. But I'm just saying that suppose we are, remember, we are now playing Dirac. So we want to follow equations, not solar winds. Okay? equations do not say anything about how lines cross here. This was imposed by hand by this force free electrodynamics. In fact, Anatoly Spitkovsky, for example, in these beautiful pictures of pulsar magnetosphere, does the same thing. In his code to force free electrodynamics, he adds a few lines saying don't dissipate Poynting flux, okay? Let's keep playing Dirac. This is force free electrodynamics. One 4-vector, one scalar. This I missed a slide. I missed one slide. Because I'm using this notation. You can almost guess. If I have B squared and E, I can form two invariants, one scalar and one pseudoscalar. So let me take one pseudoscalar and one scalar and represent these as follows. Okay? So this condition makes it a scalar, leaving this one a pseudoscalar. So these you can call proper electric and magnetic field. Okay, at any event, for any electromagnetic field, I can define proper magnetic and proper electric field. Proper electric field is a scalar, proper magnetic field is a pseudoscalar. Okay, so this then is our Ohm's law in force-free electrodynamics, which seems to be okay, but not quite, because it actually goes singular if you don't take special care. This is our strong field electrodynamics. One vector, one pseudo vector. F is tensor, F tilde is the dual tensor, B naught is pseudo, E naught is pseudo, is scalar, this is pseudo, okay, so that's fine. Okay, instead of this vector, I have this pseudo vector. Fine. Instead of this E naught, instead of this scalar, I have this scalar. Now the physical meaning. Remember, there are these good frames where E is parallel to B. Force-free electrodynamics postulates that in a good frame, electric field vanishes and current flows along magnetic field. Strong field electrodynamics. There are these good frames. Strong field electrodynamics postulates that there is the best frame of the good frames. In the best frame, electric and magnetic field are parallel, and the current equal to this value flows along the common direction of those fields. So I have done almost nothing, right? You understand? From here to here, it's just the same picture that I showed in strong. So this is then in force-free electrodynamics. This is my picture. In strong field electrodynamics, this is my picture. Okay. The reason why it took this simple thing took whatever 40 years is almost obvious, because it's very hard actually to write Ohm's law without the external velocity. Remember, Ohm's law in the metal, J equals E, requires a frame, namely the frame of rest of the metal. Here I don't have a frame of rest, so writing down this Ohm's law is hard. Now if you look at, now in the 3+1 split, which you put in a computer, this is force-free electrodynamics, this is strong field electrodynamics. In fact, strong field electrodynamics is much better, is more friendly for your computer, because it has less derivatives. Here you see all these derivatives. Derivatives are bad to have in a computer. This has less derivatives. And so in fact, for a time, some people believe that strong field electrodynamics is a good way to regularize force-free electrodynamics. And in a sense it is actually, we will come to it. Okay, so you can just put this thing into a computer, that's fine. There is only one, right, and let's keep going. So the funny thing here is that here is the claim. In fact, remember, force-free electrodynamics was too good to totally throw it away. It was clear strong field electrodynamics in the limit of high conductivity. So when this conductivity sigma is very large, actually reduces to post-wave electrodynamics. And this part is highly non-trivial. This is another indication that we must derive. Equations think for us. You see, this strong field electrodynamics as one of its equations postulates that your current is always space-like, meaning J vector is always longer than rho. Okay, this is negative or zero. So it means that current, there is always more current than charge. But this seems to be wrong because strong field electrodynamics, in particular strong field electrodynamics of pulsars, admits time-like currents where rho is greater than J.
What about the closed magnetosphere, for example?
Exactly, that's the point. So in particular in the closed magnetosphere there is rho which is greater than J, exactly. So for a while, therefore, people thought that strong field electrodynamics doesn't work. But in fact it does work. It remarkably reproduced closed field line regions by doing the following trick. This funny Ohm's law, always at each time step, it switches the sign of the of the space-like current in such a way that the average current becomes actually time-like. You see, I have rho J. Suppose at each time my J is greater than rho. But at one step it is this, at another time step it is that. J1 and J2 are both greater than rho, but their average is actually less than rho. It turns out that this is what strong field electrodynamics
And you claiming some of that is happening in closed magnetosphere?
Yes, exactly.
Rapidly fluctuating current.
At each time step, in fact. Rapidly would be bad, but in fact it is fluctuating at each time step, such that the 2-time step average is exactly what post-wave electrodynamics predicts. So now you can put this thing into a computer. In fact, it is immediately obvious that this guy is much better, because post-wave electrodynamics, if you just apply it to pulsars, it becomes singular, and you have to do tricks for stop. Strong field applies to anything. Just take random electromagnetic field and go around.
So one question about the switching. Are you saying that that's in practice what happens, or are you saying that that's...
That's what happens. It has been checked. I don't quite understand why.
No, I mean, in physically that's what happens in nature.
And even physically, it is probably what happens in nature.
Artifacts of the luminaries.
I think it is actually close to what happens in nature, because if you think about this thing, you see this requirement that the current is always, there is a lot of physics here, right? So this is again, one illustration that this must be all right is because equations think for us. So this was our prescription, but let's try to think about physics, and we will be working always in this good frame. So I have some electric fields, some magnetic fields. I have some charges. Suppose my conductivity is very high, and yet my electric field is non-zero. I have some charges, pluses and minuses. I put them into the electric field. Since my electric fields, by postulate, are very strong, they will immediately tell pluses to go up at the speed of light, and they will tell minuses to go down at the speed of light. The result will be a space-like current. Namely, it will be a current greater than the difference between the charge densities. So if you think about it even physically, if the only fields which you admit into your theory are strong fields, they will, so what happens in a code then is that once this happens, the charge separation switches the direction of the electric field, and then the situation is changed, and it switches it up. And in fact, remarkably, people who did microscopic simulations have found the same phenomenon, that for certain requirements, if you require rho to be greater than J, you have to have this switching of the, so they found time dependent. So for lack of time, let me jump to results. You use the strong field electrodynamics. This was pulsar magnetosphere. This is pulsar sphere. Here you see a clear light cylinder where all of a sudden this thing goes down and these lines become all open. Here you will have hard time finding the location of the light cylinder. In fact, pointing flux happily goes down to the equatorial plane where it gets dissipated, therefore field lines close here. And when you show this picture, say, to radio, I showed this to some radio observers at this NRA or something. They were immediately furious. Everybody knows that field lines don't close beyond the light source. This is pulsar, but in fact, strong field electrodynamics tells us that this is what's happening. This, in fact, like I have argued already, is phenomenologically very welcome. This is beyond the light cylinder, the pointing flux gets dissipated in the equatorial plane. This will produce good gamma ray light curves. This is probably where, so this would be the work surface of a pulsar, very likely. So we must end. In summary, we can tentatively claim that the first part of the yet to be developed pulsar theory has been completed. For a given distribution of magnetic field and for a given spin, we can calculate the spin down luminosity. By the way, one of the results is that this is somewhat frustrating, but for axisymmetric pulsar, dipole radiation gives 0. Neoclassical theory gave u squared omega 4 over c cubed. This thing gives 0.9 u squared omega 4 c cubed, of which 0.45 is damped in the. Okay, so predicts spin down and the fraction of spin down, which is damped right beyond the light cylinder. It also gives a tentative prediction that a fair fraction of spin down must be gamma rays plus pairs. It occurs in the equatorial plane just beyond the light cylinder, the hypothetical work surface of the pulsar. This should give good light curves, maybe not. But actually Spitkovsky with his students, based on that theory, kind of argued that this is where the emission is coming from. So this is the story, of course, is not finished. Even the first part is only hypothetically complete, or tentatively complete. What's needed now, badly needed, is what happens. So the main claim here is that right beyond the light cylinder, you have collision of two pointing fluxes. When these pointing fluxes collide, they don't do this. When they collide, they do this. They damp each other. So how this pointing flux collision should be converted into gamma rays and pairs needs to be worked out. It's a good thing that we know that it's just collision of pointing fluxes, but details are needed. If we can do these details, the outcome should be spectral, light curves, and pair fraction coming from the work surface. Maybe inside is also something happening, but at least for the most energetic pulsars, it sounds very likely at this point that for the most energetic pulsars, most of the action is the equatorial plane or its counterpart for inclined pulsars right beyond the light cylinder. And I should stop here.
So we have a couple minutes for questions. Before we get to those, though, I should mention we're going to be taking Andrei out to dinner. So if you'd like to go, contact me or Phil Boshan.
What's the distribution of E dot B?
The distribution of E dot B? Oh, you mean where this invariant, right? E dot B, right, so this thing was done, right, let me explain the question first. So you see, this is clearly the figure of merit, right? Because this E dot B, assuming that E naught is roughly known, this E naught thing is this thing which does the damping. So it's interesting to know from where this thing is not zero. It's easier for me, Chris, actually, to tell you not this product, because E dot B will be this product. Let me instead tell you what's E naught. E naught here is very nice. This is in fact how this thing was obtained. Because originally, of course, you can take this circular electrodynamics, put it into your computer, that's all I can tell you without any comments, the answer. So let me take the limit of high sigma. Then in the limit of high sigma, this is my star, axisymmetric pulsar, this is light cylinder. This is E dot B. Okay. So this not E dot B, this is E naught. This is contours of E naught in the limit of very high sigma. As I relax sigma, make sigma smaller and smaller, you develop a funny thing like this. But in the limit of high sigma, this becomes invisible in comparison to this. So the pointing flux goes here, and here it is converted. So here your electric, so many people are asking, how come magnetic, what happens to the magnetic field here, blah, blah, blah. The fact of the matter is that here the electromagnetic field becomes electric-like. Here the electric field becomes stronger than the magnetic field. And so it drives this current along the equator. So electric field ultimately wins. So I can't imagine this much better.
For your space-like current that you observe, what's the set of time scale for the variation?
Oh, in physics, yes, this is the part which is still missing. So when I say I'm so sure, there is this is the weakest part of the theory. In fact, it has been extensively, like I said. You see, now this picture, these two pictures have very different status. This was obtained by imposing some boundary conditions here by hand and by a lot of hard numerical work. This was obtained by an amateur, namely by myself, without any hard work. In fact, here I don't use any boundary conditions. This is time-dependent strong field electrodynamics. So the reason to believe in strong field electrodynamics is that it just works without any tricks and gives some unambiguous predictions. But this question that you're asking is the hardest part of it, right? Because, so for example, like here, these two things are indistinguishable. This is the answer to the first question. So yes, strong field electrodynamics nicely handles closed line regions. It reproduces, they are indistinguishable here, almost. Now, microscopic theory. To answer your question, I need to have a microscopic theory explaining the origin of the Ohm's law. But this is a much more difficult question, you understand. If you give me a piece of metal, I'm willing to tell you that J, unless it's a superconductor, is sigma times E, because this is the simplest Ohm's law, which makes sense. Here I'm giving you some Lorentz invariant Ohm's law. This is the simplest Ohm's law, which makes sense and which is dissipative and which is Lorentz invariant. What is the this Ohm's law nicely describes pulsars, and therefore it must be right. But the microscopic theory for the metal, for example, will in fact be quite difficult, right? The simplest version would be how electrons scatter on impurities, for example, right? This theory is just simply missing here, but not quite, because actually Andrei of Columbia was telling me that he was trying to do some microscopic simulations of this polar caps or whatever, and he noticed that when you go into this space-like current versus time-like current, you have only fluctuating behavior there. So there is, I think, some hope that we will get to the bottom of it. But I'm not qualified at this point. I did not look at the Barovic's results carefully enough to be sure that his is a microscopic version of the whole This thing was just
Right.
finished, so I don't know.
You know, but this sort of, I mean, for sigma, you can generalize to be a function of E.
Oh yes, it can be a function of E naught and P naught.
But I'm not sure that really fully encapsulates the behavior close to the line where you might get double layer-like structure.
Yes, I don't know. I'm just saying, I think I was honest. This was obtained playing Dirac. Whether or not is the truth, we don't really know, but it seems to work so well that it's hard to believe it's not. The microscopic theory needs to be worked out. It remains, this is the weakest point of this whole thing. If it fails, it will fail for this reason. Okay?
All right, if there are no more questions, there's going to be cookies upstairs. Thank Andrei again.